Hello everyone, welcome to another video tutorial in my channel. For those who are new here, by the way, I am Engineer J. I am a civil engineer and I am currently teaching as an engineering professor. And in this video, I am going to discuss to you one of essential topic in fluid mechanics. We have here what we call the hydrostatic pressure. But before that, please don't forget to subscribe to my channel and hit the notification bell. Now let's begin this discussion by defining pressure. Now what is pressure, by the way? Now pressure, this is the force per unit area exerted by a liquid or gas on a body or surface, with the force acting at right angles to the surface uniformly in all directions. So let's say if we have an area which is had a dimension of 1 meter by 1 meter, then we know that is 1 square meter area. Pressure there is the intensity of the force that is acting perpendicular or normal to this region. Okay, so if we draw the elevation, okay, we have 1 meter there. So that is the force that is acting perpendicular. That is the intensity of the force acting perpendicular on a 1 meter by 1 meter or 1 inch by 1 inch or like region. Okay? Now, in mechanics, we know that pressure is given as force over area and has a unit of pound per square inch. Okay? And has a unit of kilogram per square centimeter or Pascal, which Pascal is Newton per meter squared. Okay? And we also have standard atmospheric pressure, that is the pressure on the Earth's surface that is due to the air. We have 14.696 pound per square inch. Okay, so therefore we can say that hydrostatic pressure, that is the pressure due to the weight, okay, or due to the force exerted by fluids. Okay, pressure exerted by fluids such as water, mercury, oil, salt water, and like. So we have this famous law in fluid mechanics. We have here Pascal's law, which was developed by French scientist Blaise Pascal, which is according to this law that the pressure on a fluid is equal to all direction and in all part in the container. Let's say this is our container, then according to Pascal's law that the pressure on all walls are equal. Okay, so equal in magnitude. So if we have pressure here A, then we can say that we have pressure A here as well and pressure at this point. And let's say, and since we have a pressure that is acting on all sides or on all walls in the container, that would give us a force that is acting towards, okay, the force. And since we have a force, that would create vertical head of water. That is, we have increase in the height of our water. So imagine if you have a glass of water, then you try to compress that water, okay, then you notice that our water rises, and that we have H, or what we called here the water head, okay, or the pressure head. Okay, and again, this pressure head here is caused due to the force that is acting towards the wall. As what you can see here on the top surface of our container, we have three distinct openings. Okay, we have the cylindrical opening here, we have this frustum opening here, and we have cylindrical or right cylindrical opening. Okay, as what you can see, they have the same vertical head despite the orientations of our openings, and that is because we have the same pressure all throughout. Okay, so that is according to Pascal's. Now we have this gauge pressure. Now this gauge pressure, this is the pressure read by pressure gauges or manometers. Example of manometers here is U-tube. Okay, this U-tube here would give us the idea on what would be the change in the head. Again, that change in the head there would give us the pressure. Okay, later, I am going to show you the relationship between the pressure and the pressure head. Okay? So, gauge pressure, this is the pressure above or below the atmosphere. So, we have also what we call the atmospheric pressure. Now, atmospheric pressure, this is the pressure at any point in the earth from the weight of the air above. Okay? So, atmospheric pressure, this is the pressure on the earth surface that is due to the weight of the air. Okay? So, we have a standard atmospheric pressure value. We have 2,166 pound per square foot. We have 14.7 pound per square inch. Now, equivalent to the head or to the height of Mercury, we have 29.9 inches. So, therefore, if we have or if we try na put a barometer or a manometer on a Earth surface, the reading of our Mercury here would be 29.9 inches. That is the head of our Mercury. That is due to atmosphere. Or in SI, we have 760 millimeter. That is the height of Mercury. Now, for SI again, we have 101.325 kilopascal. So, these are the standard value of atmospheric pressure. Again, atmospheric pressure, this is the pressure due to the weight of the air above it. We also have what we call the absolute pressure. Now, absolute pressure, this is the pressure above the absolute zero. Now, absolute zero here, this is what we call that is the pressure in a perfect vacuum. Now, what is vacuum, by the way? A vacuum is a region or a space which is devoid of gas. That means that a region in which there is no existence of matter. So, walang matter, even gas, okay, even molecules. But in reality, we cannot create a perfect vacuum in laboratory, of course, since we have atmosphere, we have oxygen, we have gases, we have molecules around us. So, we cannot create a perfect vacuum. Again, pressure, absolute pressure there is the pressure relative to pressure in a perfect vacuum. Okay, so that is absolute pressure, and absolute pressure is given as the formula, that is the gauge pressure plus the atmospheric pressure. Okay, so that's how you compute the absolute pressure. Okay, so we have this variation in pressure, like for example, if this is our container and we have liquids inside, any type of liquid, according to the concept of fluid mechanics, the difference in pressure in the liquid between 2 points, let's say this is our point 1 and point 2, is equal to the unit weight of the liquid times the height difference or the vertical distance between the 2 points. So that means that the difference between the pressure at point 1 and the pressure at point 2 is equivalent to the unit weight of the liquid times the distance between the 2 points. So we have this formula. We have the pressure at point 2 minus pressure at point 1 is equal to the unit weight of the liquid times the difference in height. Okay? So therefore, to compute for the pressure at 2 is basically equal to the pressure at point 1 plus the unit weight of the liquid times the distance between the 2 points. Okay, so that is the formula to compute the pressure at 2. Okay, now what if we have our pressure at 1 on the surface? Okay, so if we have point 1 on the surface of our liquid and we have our point 2 at the bottom of our liquid, so we have the pressure at point 1 is equal to 0 if this is a free surface. Okay, so our pressure at 1 is equal to 0 unless if the value of our atmospheric pressure here is given. Okay, but if this is an open container, so we can say that pressure at 1 is equal to 0 if our point 1 is exposed to air. Now from the formula, pressure at 2 minus pressure at 1 is equal to the unit weight of the liquid times the difference in height or that is the vertical distance between the 2 points. Okay, now we know again that pressure at 1 is equal to 0 because that is exposed to air. Now if this is, especially if this one is open container, so we can say then that pressure of 2 is equivalent to the unit weight of the liquid times the height or the distance of point 2 from the liquid surface. Okay, so this is the formula to compute pressure at any point on the bottom of our liquid. Okay, now what if the 2 points are level horizontally? Now take note, their h or difference in height there is equivalent to 0, correct? So they do not have distance between the 2 points. So therefore we can say then that pressure at 1 is equal to pressure at 2, since again they are on the same level. Okay, so they do not have a difference in elevation from the top or from the surface of our liquid. And we have here the pressure head. Now pressure head, that is the height of a column of homogeneous liquid that will produce an intensity of pressure. So basically that is what I have said in our previous slide, that due to the pressure there would be an increase in the vertical height, and that is what we call the pressure head. And we know that pressure is basically equal to the unit weight of the fluid times the pressure head or the head. Then we can say then H or the head is equal to pressure over the unit weight. Okay, the unit weight of any fluid. And again, we know that the unit weight is equal to the specific gravity times the unit weight of the water. That is the unit weight of any liquid. Now, in order to convert the equivalent head of a specific fluid to another fluid, let's say you want to convert the equivalent height of liquid A to liquid B. Now, we know that they have the same pressure. Let's say pressure A is equal to pressure B. So therefore, they would have a different height. Okay? So the one variable there that would vary is the specific gravity and the height. So we know that this one is gamma, unit weight of A times the height of A is equal to the unit weight of B times the height of B. Then we know that unit weight of A is basically equal to the specific gravity of A times the unit weight of water times the height of A is equal to the specific gravity of B times the unit weight of water times the height of B. So we can cancel out unit weight of water. So therefore, we can say then that HB or the height of B is equivalent to HA times the specific gravity of liquid A over the specific gravity of liquid B. So this is how you convert the height of a liquid to height of another liquid, okay, with equivalent pressure. Now let's try to solve an example here. So I prepared a set of example. We have our first example here. Find the absolute pressure in kilopascal at a depth of 10 meters below the free surface of oil of specific gravity 0.75. The barometric reading is 752 millimeter, and that is in terms of mercury, or that is the height of mercury. Now, take note, we have a tank, and this tank here contains oil on this surface. So this is oil, which has a specific gravity of 0.75. Okay, now we have barometric pressure here, which is 752 millimeter, and that is the reading in terms of mercury height. Okay, now barometric pressure here is the atmospheric pressure. So barometric pressure is the atmospheric pressure. And we have the given atmospheric pressure here, which is equal to 752 millimeter in terms of the height of mercury. So the atmospheric pressure here can be computed as the unit weight of the mercury times the height of the mercury. Okay, so we have this unit weight of mercury. Now we know that unit weight is equal to the specific gravity times the unit weight of water, correct? So we have the unit weight of mercury, which is the specific gravity rather, is equivalent to 13.6. So this is the standard specific gravity of mercury. So we have 13.6 times the unit weight of water, which is 9.81 kilonewton cubic meters. So if you are not familiar with this formula, so I have discussed it in my previous lecture. So I would show you the link in the description below. Just click the link so that you can watch the discussion on the properties of fluid. So this is the unit weight of mercury times the height of mercury, which is the barometric reading, which is 752 millimeter. But again, this is in millimeters, so we convert it into meters since our unit here is in terms of meter. So we have 0.752 meters. So we have the atmospheric pressure here, which is equivalent to 100.329, and since we have meter here, so we can cancel this, and the meter squared on the denominator, so we have the unit here, kilonewton per meter squared. So we have 100.329, and we know that kilonewton per square meter is kilopascal. Okay, so that is our atmospheric pressure. Kilopascal, since Newton per square meter is in Pascal. So if we have 1,000 Newton per square meter, then we have also 1,000 Pascal as well. Okay, so that is our atmospheric pressure. But if you may ask, what this 752 millimeter mercury reading? Okay, since we know that pressure should be in terms of kilopascal, that is just the reading from a barometer or from a U-tube manometer. So we have attached here a U-tube, and that reading there, that's the difference in height. Okay, the difference in height in our mercury, that is H. Now we know that H there could give us the value of pressure by just the formula. Again, H is equal to the pressure over the unit weight of the liquid. Okay, so we have this atmospheric pressure, but again we compute for the absolute pressure at a depth of 10 meters below. So 10 meters below the free surface. So from this free surface, 10 meters down, so we have 10 meters. So we compute for the gauge pressure at this point. So how are we going to compute the pressure? Let's say this is our pressure 2. So pressure 2 is just basically from the formula, pressure at 2 minus pressure at 1 is equal to the unit weight of the liquid times the height difference. Okay, but in this case, our pressure 1 is on the surface. So we just basically need to compute pressure here by just pressure is equal to the unit weight of the liquid times the height. So in this case, we have the unit weight of the liquid, which is, we know that is oil. So we have 0.75 times the unit weight of the water, which is 9.81, times the height of, or the distance of 0.2 from the oil surface. We have 10 meters. This would give us 73.575 kilopascal. So that is our gauge pressure at 10 meters below the free surface. So we can now compute the absolute pressure by using the formula. Absolute pressure is equivalent to the pressure gauge plus the atmospheric pressure. So we have the gauge pressure, which is 73.575 plus the atmospheric pressure here, which is 100.329, and this equals to 173.329 904, and this one is in terms of kilopascal. So this is the absolute pressure at 10 meters from the oil surface. So as what you can see here, we just add the pressure at point 1. Okay, the pressure at this point is basically the atmospheric pressure and the weight or the pressure due to the weight of our oil, which is this one. Okay, and that pressure here is 100.329. Okay, so this is our final answer. And that ends the first part on the discussion of hydrostatic pressure. So in the second part of this video, I will be solving more examples. So if you wish to watch the second part, I will be posting the link in the description below. Please guys, don't forget to subscribe to my channel and hit the notification bell. Thank you for listening and keep safe.